Okay, we on Thursday we started to talk about memory architecture and how does it work and like different components of this simple processor. It's not a real processor as I mentioned. It's like a simulator because it's super simple and so it's very basic processor. So we cannot find this processor market. And this processor comes as a CPU and of course it needs I/O and memory. And the CPU is consists of data path and uh, control unit. Okay, so the data path I already mentioned, which is consists of ALU, arithmetic logic unit, and like program counter and several different registers. And you all know what is a register. If you don't, just go back and study to make sure that you know what is the register because it's very important. It's the fastest memory in a processor. And the control unit is like a manager. I called it manager. Textbook call it traffic manager. Or something like just manage the sequences of the like tasks that has been are supposed to be executed. Like okay, it's time for to move the data from point A to point B, from point B to point C. All these orders come from the control unit. So control unit manage different other components. Okay, any question? And I said that this processor has several registers. Uh, First register is called accumulator that is 16-bit and can hold 16-bit data. Okay, data comes from the memory. It's very important that we know that the memory in memory processor is 4 meg 16-bit memory. Okay, so it's 4 meg. And we already discussed in on Zoom that for 4 meg, we need 12 bit to address 4 meg. It's 4 meg or 4K? 4K, I say 4 meg, 4K. So let's go. Let me just fix this, my PowerPoint again. It's not working. Okay. It's 4K. I thought that it was mistake and 4 meg, so I tried to fix it. So no, it's correct. It's 4K. Okay, so it's 4K memory, and for 4K we need a 12 bit to address this 4K memory locations. Okay, we have MAR, memory address register, which holds the memory address. What's the size of MAR? It's 12-bit because the memory is 12-bit. I will explain all of them in detail in the next slides, but let's just go over the names and then we will discuss each part. Memory buffer register is like MBR, is a register that holds the data which transfers from the memory or before the transferring to the memory. So any data which wants to transfer between processor and memory is holding MBR, okay, before the movement. PC program counter, which is very important, like it's like heart of, not the heart, because clock generator is like heart of the process, but program counter is a counter which tells the processor and the memory which instruction is supposed to be fetched from the memory and executed. We have instruction register IR, which holds the instruction immediately before its executions. So there is a difference between IR and MBR. MBR, I said that holds the data which is supposed to be transferred between memory and processor, the data. But IR holds the instruction. There is a big difference between data and instruction. Okay, so if I okay, so if this one load address X, okay, so load address X is an instruction. This instruction moves to the IR register. Okay, so the instruction itself moves to the IR register, but address X is like address of a memory which has some data. Those data moves to MBR. So there is a difference between IR and MBR. MBR keeps the data before moving from or to the processor, but IR keeps the instruction before its execution. And we have input register, any data coming from the like devices such as keyboard and other IO interfaces goes to input register, and we have output register which keeps the data before sending to the output. Okay, so those are registers. Any question? And here is a schematic architecture of an Maya processor, which shows all instructions together. You see that we have ALU, we have accumulator, we have MBR, we have MAR, input register, and output register. Okay, these are the registers, and the control unit has IR and PC. So IR and PC registers are placed in control unit, not in the data path. Okay, but how does this system works? Let me go back. How can I copy? Okay. Okay, you see what I see here. So everything is okay. So this one is like a architecture of a processor. So let's see how does it work. Let's say I want to say load address 100. This one is an instruction. What does it say? It says that load the data which is located in address 100 from the processor to the main memory. Let's say here is address 100, for example. Here is an address 100. And there is a data inside this address, AABB. There is some data. We want to like execute this instruction load 100, which means that put AABB inside the accumulator. Okay, how does the processor perform these like instructions? The first thing, and by the way, let's assume this load address is location 15, just an example. It is in location 15. So PC, the program counter, has a value of 15. It means that the next instruction which is supposed to be executed is located in address 15. Okay, then this 15, just listen carefully, because what I'm telling now is exactly how does any processor work. Even like in i9 processor, which is the latest version of Intel processor, they have the same principle and same concepts. Okay, but so if you learn this one, you like in fact know how does any other processor work. Okay, so number 15 is in PC. So number 15, which is the address of the next instruction, which is load 100, moves to MAR. Okay, so now MAR has a value of 15. Okay, this value is 12-bit. It's an address. So MAR is pointing to this location. It's pointing to this location because the address is 15. Then after that, the processor gets this instruction, which is bunch of ones and zeros, and put it in IR register, bring it to IR register. At this moment, IR register has a value of load 100, load 100. But in the form of binary number, in the form of binary, it is a binary number, which means load 100. What then? After that, this one, so first thing is gonna happen, this instruction will be decoded by control unit. Control unit looks to the instruction, and so at this moment, control unit knows that this instruction is load, okay, because it has the information. Now that the control unit knows that this instruction is a load, in the next step, control unit sends the address of data, the address of data to the MAR. Now MAR is not 15 anymore. MAR is 100. Okay? MAR is 100. Then the processor goes to the address 100, gets the data. Because it's data, it's not going to IR. Do you remember? I said the data moves to MBR. And now it gets this data and place this data in MBR. Okay? And now MBR has a value of AABB. And last step, the value of MBR moves to the accumulator, and now accumulator has a value of AABB. And it's the entire procedure process that happen during a load instruction. Is it clear? So there are some orders. One thing that I missed, when PC is 15 and control unit loads the address 15 from the memory, it increases the PC from 15 to the 16. Just move to the next instruction. So in the next cycle, address 16 will be will be fetched from the memory to the processor. Okay, any question? I will explain one more time, but faster. Okay, because we have already, it's just, I will go over it very fast to see. So it's load 100 located in address 15. PC has the address 15. So processor fetches the data from address 15, not data, instruction, from address 15, which is load 100. Bring it to IR register. When the instruction is in IR register, the control unit decodes the instruction. Now the control unit knows that the data is load. So it knows that what to do in the next step. So now that the data is loaded, the control unit sends the 100, the address, the 100, from IR to the MAR. The new address moves to MAR, which is 100, and the data in address 100 will be fetched. Because it's data, it goes to MBR register, and from MBR register moves to the accumulator. Okay, so this is like, how does it work? Let's see how many, like of course we need a data bus and address bus. Okay, so data and address, so we have like a common bus that does all this data and address transformation. So all this transformation, close the door please. All these transformations will be will be carried out by the one single bus, which I will explain later. Okay, any question? Okay. Now that we reached to this point, let me resume recording. Okay, and now that we reached to this point, we let me fix this one and then we'll continue. Okay, so now that we reached to this point, we will see some interconnections between the registers. So like the first of all, this connection is the connection between the processor and the memory. That's fine. And there are some other interconnections between MBR, accumulator, ALU, and auto register, in register. For example, for the MBR, I already explained this interconnection. If you remember, for load 100, I said that the data moves to MBR, and from MBR moves to accumulator. Okay, so there is an interconnection. Why we don't use like a common bus to do this like data transformation? That's fine. We can use we can use a multi-purpose or multi-point bus to transfer the data. But for some of the connections, if we have interconnections, the performance will be increased. So let's see what does this slide say, and it's talking about the connections. The first sentence says that the registers are interconnected and connected with the main memory through a common data bus. So there is a data bus which connected all components and the memories together. We will see the data bus on the next slide. Okay. Each device on this bus is identified by a unique number that is set on the control lines whenever that device is required to carry out an operation. What does it mean? It says that any device, any register, ALU, PC, all of them are assigned a number. So when the control unit says that device number 5, please get this data, device number 5, let's say is MBR. Okay, so MBR knows that it's supposed to get the data. So each device is assigned a number. Okay, that's it. So each device has a number, unique number. It's the third sentence talk about the separate connections which are provided between accumulator and the memory buffer register, which we already discussed 10 minutes ago. I said that data goes to MBR, and from MBR directly goes to accumulator. It can go through bus, but why should we like move in the like longer path if we can just make it very easy and faster using using a just interconnection? And the last line is the same thing that I mentioned a few 1 minutes ago. It says that this permits, what permits? Like the interconnections between MBR and accumulator. This permits data transfer between these devices without use of the main data bus. Why? What's the reason? Because it make it faster. Okay, and any question? Okay, and here is another picture which is very important. It's a memory data path. Okay, so if we look to this, let me just try to, let me put it in the OneNote so we can zoom in. Okay, so this one is like the actual connections. Okay, the actual connections in Mari processor. You see, like there is a main bus. This one. Okay, this one, which is connected to all devices except ALU. Why it's not connected to ALU? Because ALU never send the data directly to like to other devices. The ALU only is communicating with MBR and accumulator, which these communications like occurs through these interconnections to make them faster. So if you look to this diagram, you see that each device has a name, has a number, unique number. Memory has a number 0. MAR has a number 1. PC has number 2. MBR number 3. Accumulator number 4. In register number 5. Out register number 6. And IR register number 7. Okay, so each has like identified by a number, and all of them are connected to the main bus in two ways: one input, one output. Okay, one input, one output. Then that device, for example, here for example PC, for example, if that device wants to get the data, when we want to write the data, look, they use this connection because it's one directional connection. Whenever that device wants to send the data out, use the other side of connections. Okay, so any question for this diagram?
So is this going to be like similar for even more complex architecture, or is this that numbering
You mean
sort of
the
a
like?
specific example?
You mean like the
So yes.
advanced computers?
Yeah, like a
No,
lot.
it's all completely different.
Okay, so it
This,
goes like a lot higher.
it's not like us. It did not working in this
Okay.
way. Just this basic processor has been built to for the educational purpose. The actual processor is not working in this way. Okay, maybe the processors are 10 years ago, not 10, 20 years ago, yes, but nowadays it's different. Still, they have these numbers, but they don't have MAR, MBR into registers. Completely different. Okay, in this specific example, we have these registers. If we move to like MIPS architecture, architecture, they have R registers, S registers. If we move to RISC architecture or reduced instruction set computers, they have like a register called from X1 to X15. If we move to like Pentium processors, we have like AH, ADD, BHP, BHPL, BX, DX, different registers, the completely different this way. And here is the importance of instruction set architecture. If you remember, I said that instruction set architecture is like very important part of each computer. It's the part that just connects the software side to the hardware side. So this architecture you see here has its own ISA. instruction set architecture. And in the software side don't care what is here. Okay, if you program in the like assembly language or C language, you don't care if the processor has MBR or the processor has AHDH register, because it's not our responsibility to care about those registers. Whose responsibility is that? ISA. So we write our program, and the ISA is responsible to communicate with this like registers. So each processor has its own architecture, its own registers, and its own like programming. Okay, in the hardware side. But if we learn this one, learning the other processor becomes 10 times easier because the concept is same. The concept is same. So if you move to a processor i7, it's not like this. But if you learn this one and then try to learn i7, it becomes 10 times easier for you to learn i7 because you know this concept. Okay? So, okay. So, any other question? Now that we know how the processors, how the devices are connected together, let's look to the instructions of this processor. And as I mentioned, each processor has its own instruction, which is like unknown for other processors. Okay, so each processor has its own instruction set. Okay, and the same thing that I explained, it's explained here one more time. It says that ISA is an interface between a computer's hardware and its software, which I mentioned. Some ISA includes hundreds of different instructions for processing data and controlling program units. So here is some ISAs includes hundreds of different instructions. Let's say advanced processor has 200, 300, 500 different instructions. But this Murray processor has only 13 instructions. Okay, so it's Murray ISR consists of only 13 instructions. Okay, it's simple. Questions? Okay, now let's move to the next slide, which is this one is very important. We need to learn it. Instruction. How many bits is in each instruction in Murray computer? How many bits is? What's the size of memory? 16, 4K by 16. So each instruction is 16 bits. So each instruction is 16 bits from bit 0 to bit 15. Okay, bit 0 to bit 15. This 16-bit is divided to two fields. One is called opcode, the other one is called address. Okay, the opcode field is 4-bit and the address field is 12-bit. Okay, so the address bit is 12-bit because it's enough. With 12-bit, we can address all 4K memory. Okay, so 12-bit for address is enough. So what about the opcode field? Is 4-bit enough for is 4-bit enough for opcode or no? Yes, it is, because we have 13 instructions. Opcode means instruction. Because we have 13 instructions. Using 4-bit, we can like address how many instructions? 4-bit can be address. I asked you the same question on Thursday. With 4-bit, we can like identify how many instructions? 16. 2 to the power of 4, 16. But in this Murray processor, we only have 13. So 4-bit is enough. Okay. So we assign 4-bit for opcode and 12-bit for the address. Okay, that's fine. Now, do you remember those okay, so opcode is 4-bit. Let's look to some instructions. Again, I think, let me see if I can, okay. Okay, so these are the fundamental instructions for this processor. There are 9, but still we have 4 more instructions. Okay, these are fundamental instructions. Let's just take a look to these instructions because we are supposed to know what does each instruction do. The first instruction, is load in X. What does load X means? X is an address. Okay, it's address of memory. Load X, load contents of address X into accumulator. Do you remember? Half an hour ago we already discussed it. Okay, so I showed you how does the data transfer from address X to the accumulator. Load X stores load the content of the address X to accumulator. Store X, just store the content of accumulator to address X. So opposite of the load. What does add X do? Add X, X is address in address. Add X gets the content of address X and add it with the accumulator and put the result in accumulator. Get the value of address X, add it with the value of current value of the accumulator and put the result in accumulator. Subtract X, the same thing, but just subtract it. Okay, is it clear? Okay, subtract is clear. What about the input? Input, gets the value from the keyboard. That gets the value from the keyboard and put the value in the accumulator. Okay. Output register, just output the value in accumulator to a display. Whatever is in accumulator are sent to the display. Halt just terminates the program, stop, wherever it's just a stop program. Skip condition, which is most complicated instruction in this super simple processor. It's not actually complicated, but comparing to the other instructions is complicated. Just skip next instruction, on condition. What is the condition? We will discuss. If a condition is true, the next instruction will be skipped. So if we are in, if this is address 10, 11, 12, 13, 14, and in 12 we have skip condition. And if the condition is true, and at this moment when this instruction is executing, the value of PC is 13 because PC is pointing to the next instruction which is supposed to to be executed. If the condition is true, 13 will be skipped and the PC will be changed to 14. Okay, based on condition. So if the condition is true, the next instruction will be skipped. Okay, we will see some examples. And jump X, load the value of X to the PC. So if we go jump to 200, it means that the next instruction which is supposed to be executed is 200. Okay, So this one is like this one is like 9 instructions, and each instruction has an instruction number. Each instruction has an instruction number which is same as opcode. Same as opcode. So in the opcode field, if you remember, opcode field was 4 bits. Okay. So in opcode field, if it's 0001, the control unit understand that this instruction is load instruction. If the opcode field is like 0110, the control unit knows that this instruction is output instruction. So based on this number, the control unit knows that what kind of instruction is that, and so does the like necessary comments and order sends the necessary comments and orders to the other registers to perform this instruction. Okay, so if we return to the same story that I explained about load X, in I showed you like how does it work, and I said that load 100 goes to IR and get decoded. What does it mean? It means that the like control unit looks to the opcode field, see that the opcode field is 0001, and now it knows that this instruction is load instruction, and continue like the necessary steps. Okay, any question? Okay, here we have an example. We have an example of load instruction. Load instruction, first let's go back to this table. What is the opcode for load instruction? 0001. So definitely the opcode field should be 0001. So 001 is like the opcode, and the other 12 bit are address. What is the address? It's address 3. So it means that processor, dear processor, please get the data at address 3 and place that data in accumulator. Okay, so this in like code, this zeros and ones, 001, 001 means that processor take the data of address 3 and place it in address place it in accumulator. But processor is not a human. We cannot talk to processor like this. So processor needs only understand voltages and signals on wires. So our job is to build some signals, some wirings that make the processor to do this job. Okay, it's our responsibility to design it. Okay, so far I say, okay, processor do this, do that. Okay, it's not this simple. The processor doesn't know what does it mean. So we know based on these signals, we should design a circuit, a complicated circuit, some interconnections. Those signals in connections that gives the output of what we want. And the output is like the data copying from get copied from the address 3 and placed in address uh, placed in the accumulator. Clear? Any question? So don't think that it's done. It's not done. We are in charge of designing the connections, the circuits. Okay, so for example, if I want to tell the processor, please store the data the data of the accumulator in address 100. Okay, so if you get this question in like in one of your exams, and I said what's the like binary or hexadecimal value of the instructions store 100, how should you find the answer? It's easy. go back to this table, find a store. What is the store opcode? It's 0012. So go back to your question. So say 0012, and the rest is address 100. Okay, I should have told you this 100 is hex, binary, or what kind of data is that? Okay, so let's say it's like, let's say it's just any number. It's we convert it to binary and place in 12-bit. Okay, so and this information is representing the like this instruction store 100. Clear? Questions? Okay, good. Next, move to like okay, so we know how does store load store works, and if I say for the same thing for add and subtract, the same thing, and the like escape condition is here, which, as I said, is the like most complicated instruction for this processor. The first of all, let's look the opcode of a skip condition. The opcode of a skip condition is 1000. 1000. So we need to say, okay, the opcode field is 1000. The skip conditions doesn't use the entire 12-bit of the address field, because the skip condition doesn't refer to the memory. When we talk about the load instruction, of course we say that, okay, go to address X and load the instruction. When we say add, we means that go to the address X. When we say jump to address X, again we're referring to an address. But a skip condition is like one of those instructions. There is one more instruction doesn't refer to memory. Do you remember? From those 9, one of them doesn't need like to terminate the program halt. Yeah. So it's just halt. So the address field is empty. Okay, we don't care because it's halt. Just stop wherever we are. Okay, but the others are like needs address. The step condition also doesn't need address. Okay, the only so from this 12-bit of skip condition, from this 12 bits of skip condition address, the only two of them are being used. Bit number 10 and 11. 10 and 11. So I would say the others are always 0. So from 0 to 9 are always 0. Okay, even if they are not 0, I think it doesn't affect the processor, because the processor doesn't just check those values. The opcode field, which of course should be 100, 1000, and these two addresses, these two bits, bit number 10 and bit number 11, are important. Bit number 10 and 11 like can be combined in 4 different ways, and why we use how we use this one, let me see, where do I have it? Let me show it here. Here is like the skip condition system. How does it work? It says that if this one is like this one is let me just first talk about RTL, and then I will talk about that slide. Okay, so these two bits, bit number 10 and 11, determines a condition. If that condition is true, we skip the next instruction. That's enough for now. Okay, for now it's just we need to know that bit number 10 and 11 are a condition. If that condition is true, the next instruction will be skipped. That's it. Okay, so but how does these instructions are executed? If we go to assembly language, then we move to this machine language, which we already have. And each of these instructions, itself consists of the sequences of smaller instructions. Do you remember I said load X? Load X itself consists of smaller instructions. Those smaller instructions are called micro operations. Okay, micro operations. So each instruction consists of several micro operations. Okay, so the exact sequence of micro operations that are carried out by an instruction can be specified using register transfer language. Register transfer language, what is the difference between register transfer language and uh, like the instructions? Let me tell you what's the difference. This one is an instruction, load X. Load X, we know that load X gets the data in address X and put it in accumulator. Do we know how? No. Just we know that what does it do? It gets the data from the memory, places the data in accumulator. But RTL language, which is for micro operations, directly work with those with those registers. So it says that okay, place the like the MAR in like address, get the data from address memory, put it on IR and get the data from IR, place it to MBR. So it talks about in the like register level. Okay, so if I go back to my I don't know where is it, here. Okay, I'm happy that I found it. So if we go to here, load 100 is instruction assembly language in instructions, and all these transformations, all of them I explained to you, which data moves from which point to which point to which, are in RTL language. Okay, RTL language is in the like in the register level. Just tells okay, data from PC moves to MAR, from MAR gets to memory, and from memory go to IR, from IR go to MBR. So this language which deals with them like with the registers is called RTL. Okay, let's go back to this slide. Okay, so in RTL, we have a notation. The notation like M bracket Y. This Y is like an address. Y is an address, okay? It could be X, it could be Z. Just M bracket Y, what does it mean? Here is like, it says, what does it mean? It says that M bracket Y, okay, indicates the actual data value stored in the memory location Y. Okay, memory location Y. So if we go back to this one, can you tell me what is M, what is M100? AABB. Very good. And can you tell me what is M? So if you see M100, it means that go to address 100 and whatever is 100. So what is M15? What's that? Oh yeah, a lot. And can you tell me like the assembly, just a number 0001 100, because we know, and we can convert it to like hexadecimal and like the number. Okay, so it's exact like M bracket any address is like a notation. Okay, it's very important we know to know that, because we want to write our RTL micro operations using that notation. And of course, we have an arrow. The arrow means like the transfer direction. Transfer direction. So if we say my like this, AC to my, it means that the data of accumulator moves to, we cannot say AC to my, but because it's not connected to my, AC is not connected to the data. But if we say MBR to my, it means that the data at MBR will move to this location. And if we just reverse the direction of the arrow, it means that the content of content of the memory at content of the memory location Y will be transferred to the MBR. Is it clear? Okay. Now let's see some micro operations for some instructions, and we also make it more complicated. So this one is not 100% complete micro operations. It's not. Okay, we need to add some like more lines, but let's move step by step. So the RTL for load instructions. Do you remember load for this instruction? Load X. For load X, this one is the RTL. So load X in RTL language can be written in this form. How we can just interpret this one, how we can just deal with this instruction language. We say that X goes to MAR, as I mentioned. X goes to MAR. X is an address. Goes to MAR. The data of the data of the memory with MAR, which is the instruction, which is the data, will be moved to MBR, and MBR moves to accumulator. Okay? So one more time. X, the address of the data, moves to MAR. That data moves to MBR, and MBR moves to accumulator. Okay, so what about add? What about add instruction? Add X. If you remember, for add X, I said that add X gets the data in address X and add it with accumulator and place it in accumulator. So how does it work? Address X will be copied to MAR. The data at that location will be moved to MBR. MBR will be added to accumulator and placed in accumulator. That's it. MBR will be added to accumulator and placed in the accumulator. Okay, so the only difference with the load is in load we just load MBR to accumulator, but in add we like add MBR with the accumulator and place it in the accumulator. Okay, so can you tell me a case? Can you tell me a case that load X is identical with add X? Very good. Perfect. When the accumulator is zero. When the accumulator is zero, no matter if we use load X or add X, because add X also gets the data and add it by zero and place it. Great, very good.
MAR arrow X, that's a micro operation itself, but no.
Could you repeat the question?
Like the MAR arrow X are all those instructions there. Those are all micro operations.
Just micro operations, yeah. Each is one micro operations. This one, we show it with micro OP. Okay, micro operation number 1, number 2, number 3. So the load X is like consists of 3 micro. In fact, it consists more than 3. But I try to go step by step. Okay, so great, good answer. So the add and like load are exactly identical if the accumulator is 0. Any question? Okay, so next let's look to skip conditions, which we want to see how does it work and what are the micro operations for skip conditions. Okay, so if you remember, let me change the color of my how can I change the color of, okay, that's fine, black is fine. So let me full screen it. Full screen. Okay. And how can I change the color to red? Okay. So here we have the micro operation RTL. Instead of micro operation, I call it RTL for escape conditions. I said that we looked to bit number 11 and 10. No any more address field. If it's 00, if it's 00, if it's 00, and then if accumulator is less than 0, then we skip the next instruction. So one more time, if bit 11, 10 and 11 of the address field is 0, we check the accumulator. If the accumulator is negative, then we skip the next instruction. How we can skip the next instruction? I already mentioned it. We add 1 to the PC. So PC always pointing to the next instruction. If we add it by 1, it skip and goes to the instruction after the next instruction. Okay, so 00 is if accumulator is less than 0. 01, 01 if checks the accumulator. If accumulator is 0, then jumps, skip the next instruction, and then the next condition is 1 1. For 1 1, it checks if accumulator is greater than 0, skip the condition.
So if you're just incrementing the PC, wouldn't that instruction still be in memory? What like then removes it from the memory?
We don't want to remove it from the memory.
Okay.
Like it's like I'm sure that all of you have done like programming. Sometimes you for programming you said if like let's say you say enter a number, for example, on my keyboard, and I enter a number between 1 and 10, and I enter a number 4. And next line it says that if the number is less than 5, jump to this location. If it's greater than 5, jump to other location. Okay? So sometimes, based on the data in the accumulator, sometimes we skip the next instruction in the memory, sometimes we don't, depending to the input. Depending to the input, sometimes we like skip that info data, sometimes we don't. When we write the actual programs, you will see that. Okay, so it doesn't mean that these conditions are not true always. Okay, sometimes based on the data, sometimes there are true these conditions, sometimes there are false. Okay, based on what? Based on some previous calculations, inputs. So if you run the program 100 times, let's say 50 times, the conditions are true and we skip, move to the next instruction. So that instruction will be skipped. Another 50 times, the conditions are false and the next instruction will be executed. Okay? So, and if I understood it correctly, you mean that if we are in escape, we have escape conditions in this location, and let's say location 100. In location 101, we have something I don't know. Let's say x x y y something I don't know what's that. And in 102 we have add two numbers x and y. So you mean that your question is that if we move from 100 to 102, what's going to happen to 101? 101 is like still in the same location for the next time we run the program. So it's like the main program. So the source information doesn't change. The instructions doesn't change. The only thing that we can modify, we can just override all are the data, not the instructions. Okay, so we cannot override the instructions. Each memory consists of two parts: data and instructions. Each memory. So these instructions are like loaded when you install an application on your cell phone, these instructions are loaded. So they're loaded. You don't change them anyway. Okay, but those data are something that you just work with them, you override. So this line 101, which I show you, it's XXYY, is like an instruction. We just skip it. That's it. It's still in the memory. You got the answer, or
Yeah,
still? It's,
it makes sense. What if bit 11 and 10 is 10?
we don't have that condition. Yeah. So it's something that we, when we program, it's not part of our program.
So with the structure, you have like IR bracket 11 minus 10. Is that saying from like bits 11 to 10?
Bits 11 to 10. Yeah. So if I say bit 11 to like 9, it means 11, 10, 9. Okay. But here is just 11 and 10. Any other question? Okay. So, so this one is a skip condition, which we need to know how does it like work. And here, kind of like in review. So let's just read it together and see what does it say. I believe that I mentioned all of this like notes, but let's see what do they say. It says that the fetch, decode, execute cycle is the series of steps that a computer carries out when it runs a program. Okay, we know that. Okay, fetch, decode, and execute. Okay, in our example, fetch was when we get the data from the memory placed in IR. Fetch. Decode means the control panel checks that opcode field to see what is the instruction. And execute means like the actual work, the actual like calculations. Oh, we first have to fetch an instructions from memory and place it into IR. So again, I mentioned it 2 times, and this one's the third time. When we fetch instruction, not data, when we fetch instruction, we place it in IR, not MBR. MBR like only holds data. Okay. When we fetch the instruction from the memory, it's like placed in IR. Once it's IR, it is decoded to determine what needs to be done next. Just check that like opcode field. And then if a memory value is involved, why I'm saying that the memory value is involved, like load and subtract. But for some conditions, for some instructions like skip, halt, we don't have any memory involvement. Okay, so it's the reason. If the memory value is involved, uh, it is retrieved and placed in MBR. This time, the data from the memory goes to MBR. So instruction moves to IR, data moves to MBR. Main difference. And then when everything is in place, the instruction is executed. Okay, so it's like a general overview on the instruction processing. Question? Okay. And this one again shows an instruction processing which has more details compared to those RTL that we discussed. So I will show it and I will explain to you what's the okay. How does it work? We'll start from a start point, okay, from a start point, and after a start point, we copy the PC to the MAR. Do you remember? We copy the PC to MAR. Let me just show you one thing. If Okay, so I want to show you this one. Uh, this one. When I was completing this processes, do you remember what was the first thing I put there? Which arrow was the first one? Which one was the first step I did? MA. The first thing I did. Say it again. Exactly. The PC moved to MAR. 15 moved to the MAR. Exactly. The 15, the address moved to MAR. This one was the first step. Okay. So it's here. Exactly the same thing is explained in this flow chart. Copy the PC to MAR. Exactly the exact thing that I did, like by drawing arrows, is like here in the flow chart. Okay, so the PC will be copied to MAR. The next one I draw there, it's the one that it was the copy the content of the memory. Content of the memory. Can you tell me this content of the memory is instruction or data? This content of the memory is instruction or data? Instruction, because PC puts the next instruction address to MAR. So the content of memory, it's instruction, not data. The instruction moves to IR. Why to IR? Because it's instruction. Okay. And one thing that I missed in my like schematic and I showed it at the end. It was increment PC by 1. PC will be incremented by 1. Then the next thing I said that the instruction will be decoded. Will be decoded by IR, decoded by control unit, and IR 11 to 0. This question you asked me, you said that the IR 11 10 means 11 to 10. Do you remember? So 11 to 0 means that IR 11 to 0 will be placed, will be like a copy to MAR. Okay. Then we move to the next part. Next part says instruction requires operands. Instruction requires operand means that do we need to access to memory or no? Which instructions like don't required operand, halt and escape. Okay, so if we need, let's say for now we need operands like load. If we need copy the content of the mode, this time this content is data. If you remember, here I said it's instruction, that content, but this content this time is data. This content is data will be placed from MAR because its data will be placed in MBR. Okay, and next like step we will execute the processor will execute the instruction. Okay, and repeat, go back to the like a start point and fetch the next instruction. Okay, and by the way, I reach to this point and move downward. What if the instruction doesn't require any operand? That's fine. We directly execute the program. We don't get any operand from the memory, like halt or skip condition. We don't need to access to the memory. Okay, so this one is a flow chart of this processor. Questions? Okay, we already talked about the interruptions. I think it was in one of our online lectures. Interruptions means like here I'm talking to you, someone knocked the door. So okay, so there are two ways. If somebody knocks the door, is it maskable in interruption or non-maskable? Like
You can ignore.
I can ignore. Okay, I can say okay, that's fine. Okay, unless it's like department chair, I can't ignore. Okay, so but I can ignore. It's maskable. But if the fire alarm goes off, is it maskable or unmaskable? It's non-maskable. We have to run out because it's non-maskable. So some interrupts are maskable, some interrupts are non-maskable. Okay, so depends to the. So the interrupts like can occur in different ways. Sorry. Like we have a user break, like when you have a like running a program, you can click on exit or Control C or escape, just stop the program. There is a like user in like user break. I/O requested, which you have connected an I/O to the processor, and an interrupt comes to the like to the processor, and we have a critical error, as I said, like dividing by zero, or some like interruptions that are we cannot mask them. So these are like kind of interrupts that we deal with those interrupts. And here it says that the software interrupts are also called traps. That's the name. Okay, that's fine. So these are different type of interrupts. So when does this interrupt like happens? It says that interrupt processing involves adding another step to the fetch, decode, and execution cycle as shown below. Okay, I hope that I can copy it. Let me see. No, let me full screen. Okay. Okay, I believe that you see now. Okay, so it says that every cycle, every fetch, decode, and executions. Before moving to the, like any of those steps, first we check to see has an interrupt been issued or no. Okay, has an interrupt been issued or no? Then move to the next step. If the interrupt has been issued, we process like the interrupt. We like respond to the interrupt. If the like interrupt hasn't been issued, we perform fetch, decode, or execute cycle and continue like the next cycle. So every time we want to start any uh, instructions, at the beginning we check for the interrupt. If the interrupt has been issued, we stop at that point, move to the interrupt routine, and run the interrupt, respond to the interrupt. Otherwise, we continue our instruction. So on the right, you see there is a perform fetch decode execution cycle. You see like a rectangle on the right. So that rectangle is like all of this chart. Okay, so if the interrupt is not issued, then we start to do this like process. Clear? Questions? Okay, so I stop recording.